So now it's my great pleasure to introduce Andy Zeng as our last speaker today. And Andy is a senior research scientist at Google AI working on computer vision and machine learning for robotics. He received his bachelor's of computer science and mathematics at UC Berkeley and his PhD from Princeton University. And he has won several prizes. One of them is the Best Paper Award at TRO and the Best Systems Paper Award here at RSS. And was a finalist for many Best Paper Awards. And I think his research is really interesting. He's done throwing around objects, thinking of deformable objects, and always with the computer vision and the robotics view in mind. So I think he's the perfect person to talk about representations and to wrap up this work. So please join me in welcoming Andy in this session.
Thanks for the introduction. Today I wanted to talk about, or the title of my talk is talk about representations, and it's a little bit of a play on words, and hopefully later down the talk it'll start to make a little bit more sense. I thought I'd start off a discussion first, just talking a little bit about tossing bots representations. So for just a little bit of background, tossing bot is a system that we built to throw objects, and this came out of a observation where we were going in industry warehouses and we saw that robots were generally moving in relatively rigid motions. Whereas if you go to a real warehouse and you see a person doing the task, they're oftentimes fluidly, dynamically moving objects around, tossing things all over the place. And I think that what's interesting about this is not just the efficiency, but also the reach range. So this person was able to basically cover, be able to effectively manipulate things that are outside of her effective reach range. And if you ask Amazon, what is one of the most expensive things about putting robots in warehouses, you might find that the answer is not actually efficiency, it's actually space. Humans, for the amount of labor to space footprint, actually is, humans are just incredibly hard to beat. We went back into our lab after observing this, and we wanted to see if we can also get robots to toss things. And it turns out that they're pretty good. And it was very surprising to us also that decades of hardware research sort of landed on systems where you can essentially have industrial grade repeatability on some of these tasks. So for example, you can quite reliably, and I think that the video is lagging a little bit here, but you can quite reliably, repeatedly toss a pen into the cup over and over again. Which is pretty exciting. Being able to toss the same object is relatively easy, but being able to toss very many different objects is relatively hard. And this is because different objects have different dynamics that you need to deal with. And so we were interested in how can we learn this through trial and error, and eventually came up with the system tossing bot. There's a system architecture behind all of this, and it's taking in RGBD images as input, generating an orthographic projection, and feeding that into a fully convolutional network to predict two things. One is a dense heat map of grasping affordances, and two, throwing velocities. One interesting thing about this particular architecture is that every pixel represents a different action that you can execute, where effectively your state that's going in as input to your implicit grasping value function is the effective receptive field of the network. I'm describing this architecture here because specifically I wanted to get to the point in which we had this inside of the appendix of the paper, but I think it was a little bit under highlighted, which is what did tossing bot actually learn from doing all of these interactions over time. And it turns out that, so we were supervising grasping affordances as well as throwing velocities, but what was interesting to us was looking at some of the features and how they clustered with each other. So there's no explicit supervision on what the semantics of the objects could be, but over time you start to see that the features naturally cluster towards things that are semantically meaningful to specific objects. For example, if you took a pixel that belonged to a ping pong ball, you would immediately, and if you tried to visualize the nearest neighbors among all of the other sort of pixels that belong in the scene, you'll start to see that they cluster around the other ping pong balls in the space. And this is not just trying to predict similar colors, because if you look at the blocks that are colored orange as well, they don't really fire up in the visualizations here. Similarly, if you took a marker pen, presumably because throwing a marker pen is relatively different than throwing a ping pong ball, you start to see these visual features naturally arise in picking up all the marker pens that are inside the bin. So this is exciting because this shows that the power of these features, they ended up going beyond ImageNet features that we were looking at. That's what this figure is trying to show here. But what was interesting is that we've always thought that we needed to develop these semantic segmentation systems in computer vision to really use that as a conditioning mechanism for our downstream control. But what we're seeing here is that as we're learning the control, these representations start to naturally arise. I think that this kind of representation that we saw in Toussaint is part of a broader hunt, I think, in the community for what is the best state representation that we should provide for our robots. We have learned visual representations, and we've seen a lot of interesting work in this workshop as well on how we can learn representations through dynamics, or whether it's through self-supervised objectives like contrastive losses. There's also various different 3D representations that folks have been playing around with, like Vincent's talk, NERF representations. There's also explicit 3D reconstructions. And also in some of the work from Zhao Jing's lab and Rohan Gao, Zeng Si, and Yunzhu Chang on multisensory representations. How can you extract interesting, meaningful information from different modalities? And also, there's also interesting sort of state representations that can naturally arise when you're trying to pull the information from actions. For example, if you were trying to do continuous control, you have continuous time representations that you can also integrate over time. Or if you're also predicting affordances, then maybe perhaps you can use ImageNet as a way to extract meaningful representations into those affordance models, and as well as maybe potentially learning these representations from just mass corpuses of videos from YouTube. But ultimately, the thing that we're really concerned about is how do we represent Z? Z being the latent space or the state representation that we're after. And I think that maybe we don't directly put it in our papers, but I think what we think about a lot is how can we make this Z as semantic as possible, as compact as possible? Can it be really general? Can it go to different tasks? And can it be interpretable? And hence all of the beautiful TSNE figures that people create from the later state representations. So I think that I have a proposal for the crowd here, and I think that this potentially goes potentially controversial at this point, but I think that we're starting to see some interesting evidences that pointing to us towards this, which is, what if we think about language as being the state representation? And one sort of immediate thing is that if you think about it, language is developed, over thousands of years of people socializing, and over time has resulted in something that's semantic, compact, general, interpretable. And another thing is that I think on one side, we do have, of course, advent of large language models, which is why we're starting to think about this a bit more. But at the same time, I think there's little pieces of evidence inside the multitask learning areas of literature that are also starting to point that maybe this could have been potentially the multitask representation that we've been looking for all along. And to kind of dive into that a little bit more, so whenever I think about generalist robots, I'm constantly thinking about a robot that can do many tasks. And so oftentimes I'm reading through multitask learning literature to kind of get a little bit of inspiration. The one question that everybody's excited about is, does multitask learning result in positive transfer of representations? And I think sort of over the last couple of years of research sort of suggests that it's complicated. I think, for example, in computer vision, there's this wonderful paper written by Amir Zamir, Alexander Sachs, William Shen et al. On taskonomy at CVPR. And what this paper shows is that if you pre-train on task A, they wanted to measure just how much it would influence on task B. So you can imagine this massive affinity matrix where red means that it doesn't transfer well and white means that it transfers well. So what's surprising is that the assumption that you can train on any task A and it would improve task B is actually much more subtle, because if you train something like an edge detector and then fine tune on depth segmentation, you don't actually get sort of the best trade-offs here. You might actually deteriorate in performance sometimes too. So this was an interesting finding, and this affinity matrix has in general been very useful for research down the line and people picking out which tasks they want to use as pre-training. In robot learning land, I think there was this interesting paper from NeurIPS 2020 from Sam pointed out on the magical benchmark. And specifically what this was doing is looking at how can you learn continuous control inside of these simulated settings. And specifically what's interesting is that in the tables, you'll find that they also evaluate on a multitask agent. You have 10 different tasks that you can train these agents on. And if you group up all of the tasks together and train them on one large data set, you actually deteriorate in performance. So if you look at the numbers, multitask, this particular row here, actually performs worse than if you were training BC on this, the same task, and this is with the same amount of data. I think likewise, we're also seeing in the most recent Gato paper that's coming out, which is that it's such an amazing system that's capable of training on so many tasks, but at the same time, the amount of performance that you can achieve is still roughly on par with some of the previous BC baselines. So positive transfer is still relatively challenging to achieve. But one interesting part, and this was pointed out by my colleague from Google, Pete Florence, is that actually, if you look at a recent paper that came out, Clipboard, and I think that it was also fell under the radar for a while, but I feel like I'm starting to pick up on it again, is that they have actually experiments that are showing surprising results, which is that multitask learning, when you ground it in language, actually seems to be more likely to lead to positive transfer. So a little bit of a background on Clipboard. This is not my work. This is Mohit Sridhar, Lucas Manoli, and Dieter Fox. And this is from Coral last year. And specifically, they were doing language condition pick and place tasks. And if you go to their website, they have some incredible results. They also have real world experiments. And one of my favorite experiments is where they literally put sticky notes of good and bad inside of 2 boxes and had the system be able to sort between the 2. And that's just fantastic. So the main idea is that you essentially can condition a lot of the various different pick and place tasks on language instructions. And it turns out in their paper, and this is their a really big table, and there's a lot to take in, but I think the one that I want to guide your attention towards is the row which shows Clipboard with multitask. And this is highlighted in green. Specifically, what you'll see is that the predominant amount of bold numbers that appear there with the multitask actually outperforms Clipboard just trained on single tasks. So this was actually one of the first times in which I personally have seen really solid positive transfer coming out of multitask training. And it feels like there's possibly possible explanations for this could be that when you have this language conditioning, you're naturally trying to focus semantic attention onto the things that matter. So if you had an end-to-end learning architecture, you might just, the model architecture might initially just pay attention to random sporadic features that are in the image. But once you're conditioned on language, it starts to coerce itself into paying attention. Oh, the red pixels actually belong to the red block, etc. So I thought this was very interesting. And also, if you go into the original CLIP paper as well, you'll find that they have this, again, massive table with lots of numbers. But the point here is that every column is essentially a different computer vision benchmark. And with CLIP, as pre-training, you essentially have state-of-the-art numbers all across the board, which is absolutely outstanding. So what this tells me is that potentially, and maybe this is, will be falsified a couple years, or maybe it'll be true, who knows. But really, I think that some of these pieces of evidence are pointing us to the fact that language is a way in which we can start to coerce these models to kind of overlap on and be able to pay attention to the things that are important, or at least what we humans consider important, just by de facto being a representation that we ourselves as humans have used for communication for such a long time. So a question now is, how do we actually use language as a state representation? And I'd like to, it's still an open research problem, I think. There's lots of different ways to do it, but I think here's one way that I'd like to talk about. And specifically, this is from a recent work from our group called Socratic Models, Composing Zero-Shot Multimodal Reasoning with Language. The main idea here is that you effectively, for example, have a pick and place setting and you have a robot on a workspace. And the idea is quite simple. You take a visual language model, and this could be out of the box from CLIP, Align, Lit, Veiled, or MDETR. These can be open vocabulary object detectors, and you're literally using them to construct a description of the scene. In this case, it's just a list of different objects that it sees. And then you can take in as input human instruction, which is kind of highlighted in pink here. You can feed all of that into a large language model for planning. So it'll take the human instruction and break it down into different tasks. And then for every subtask, it feeds that into a language condition policy. So that could be clipboard, for example, which is what we do in our case. I think this is somewhat interesting because the whole thing is basically operating on language. And I think the key thing here to pay attention to is how we're representing the state of the environment. Here, it's just a list of objects, but there could be other ways to describe the scene in the future. So I thought that I'd do a little live demo actually also just to show a little bit of some of the capabilities that are here, and this is all open source as well. So I'll point y'all to some of the code here. So specifically, what I'm doing now is that there's on the server side, there's a PyBullet server, and this is running a environment with a robot over a workspace. And what we're doing is the first step of the pipeline, which is running val to detect objects that are in the scene, and that's giving us a list of descriptions that we should feed in. So some of the cool things that you can do with the system now is you can literally type things like move all the blocks to different corners clockwise. And what it'll do is it'll first use a language model to generate a list of different steps, and then for each step, it's going to pass it to clipboard, and clipboard will execute the actual action on the server side. Once it executes it, then it'll render out a bunch of images and visualizations for us to see what's actually happening. So this step, the language model predicted, oh, pick the yellow block and place it on the top left corner. So it does that. These are heat maps, picking and placing heat maps that are predicted by clipboard. And this is the actual robot rollout view in PyBullet. It does that. So it's going to break this down into 3 steps. The second step is pick the green block and place it on the top right corner. So it's going to go ahead and roll that out. So you'll see it play out in the video. And then finally, the last video here, picking out the blue block and placing it on bottom right. So it's placing all the blocks to all the different corners clockwise. That's cool. But you can also say things like now move the forest colored block to the middle. Oh.
No.
Oh. Oh well. I guess it's still denoise. So language models, they have a fairly interesting capability of denoising. But the point here is that forest is a forest color. That's something that maybe previous systems like Shurglue that some people compare the system to cannot do, because forest is just, there's some contextual information that it's green. Anyways, okay, great. So I put the stuff into the middle. We can do something like stack the blocks with the banana colored one sandwiched between the other 2. Okay. So here it's picked up the yellow block, placed it on the green block, and then now it's trying to do the rollout for the other pick and place action. Yeah, placing the blue block on the yellow block. And that is indeed the banana colored block in between the sandwich. We can also say, wait, actually undo that last step. The vast majority of the time it takes for this system to run is actually just rendering the video and then sending it over Colab. So if you have this system running on your local server, it'll run much faster. Okay, cool. And then we're going to, I think for the next one, what I want to do is I want to go to Google Translate. And I want to take my next command and convert it to German. Put the yellow block in the bowl you think it best fits.
You have German speakers here.
Great. So now that we have German, we can put it into the model too. So these language models, they've been trained on lots of languages too. So they just naturally know how to process semantic information. Yeah, it's generated a plan, pick the yellow block and place it on the yellow bowl. And it'll output something, I think. Cool. And then, of course, we want to show that it has some contextual reasoning capabilities as well. So we've told it to put the yellow block in the bowl, but we can also say, okay, now sort the remaining blocks in the same way. Pick the green block and place it on the green bowl. Cool. And then the next step, pick the blue block and place it on the blue bowl. Great. Okay, so it's done the task. It's sorted all of this is the before and this is the after for this last step here. So if you want to download this code, quick pitch, socraticmodels.github.io. There's a link there, code, and you'll find it on the last link here. Okay, so what's interesting about this system is one particular hypothesis that we have is that we've been constantly thinking about describing the visual world with 3D representation. There's potentially capacity here to try to describe the visual world with language. So one thing that we talk a lot about in the paper is language as an intermediate representation for a lot of hard problems that people have been thinking about for a while. Specifically, one example here is video question answering. A lot of people are trying to process information from various individual frames in a video, condense that into semantic representations, and then train on a data set of question answering. One thing that we started playing around here is video understanding as reading comprehension. So how we do that is we take individual keyframes inside the video and we generate these captions for every single image. And we append them inside of a form of a time step log. And what that generates is language-based world state history. It's in the form of event log here, but really it's just a short story that describes what the video is about. You can then feed that into a large language model, which are really good at short story question answering, and you get a lot of interesting video question answering capabilities for free. So, for example, when did I last wash my hands? And then I last washed my hands at 3:24 p.m., etc. So this is exciting because this is really taking a traditionally very hard problem in the computer vision domain and trying to pull that out and put it into a domain where we know things potentially could work more promisingly. So I think that if we can do more of that, that would be very exciting. One interesting perspective is that, at least in robotics, we often have various different modules, perception, planning, and control. And one thing that I'd like to propose to this community here as well, as we're thinking about different implicit representations, can we also think about how we can ground some of these representations on language as well? And I feel like with language as a centerpiece, we might have quite a bit more capacity to be able to generalize based on some of the things that we observed over time. And I think another thing that's quite crucial to this is that if we ever want, for example, humans to interface with our robots, this is a very natural way in which we can just suddenly be able to not just be able to do task specification, but also be able to see internally what the model and the system is doing. It's interpretable in the way that we want it to. So quote unquote analysis mode for those that have watched Westworld, I think that would be incredibly exciting. So I think that this is not a path just for achieving potentially general robots, but also for human-centered robots. So this is an opportunity to sort of merge these things a little bit more tightly together. I'd like to close off with some of the limitations of language as an intermediate representation. One of the things that we're definitely losing out on is spatial precision. Like there's like, if we can, being able to describe something to really high fidelity as NERF can is incredibly difficult. Also, it's highly multimodal, so there are lots of different ways to say the same thing, and it's relatively difficult to kind of, if you're training language condition policies, you kind of have to make sure that that multimodality is being handled in some way. Not as information rich as in-domain representations, like images. So an image is worth 1,000 words, I concur. it's pretty expensive to kind of use that to represent images going into a language model. So I think that for this community, at least, I think perhaps this is where other representations could potentially help us. And I'm very excited about sort of thinking more along the lines of how can we take, whether it's NERF representations or 3D reconstructions or any other sort of representations that we've been looking at recently and trying to tie them together with language a little bit more. And I think that we might just be able to get a lot of the properties that we've been trying to pursue with intermediate state representations. And with that, I'd like to thank all of my collaborators, some of whom are in this room, for example, Vikas. Yeah, I think, oh, and also Igor is up there too. So yeah, thanks for having me.
Thank you so much. I could not have thought of a better talk to wrap up this workshop. Are there any questions from the audience? You were first. Okay. No, you. Yes.
Hi, thank you. Is it okay? Okay, thank you, Andy, so much for this awesome work. I'm very surprised how well it works. But I agree with you that language is very good at representing like long-term plans at an abstract level. But I also believe that this is a very human-centric way of representing the task. But a lot of crucial motor and visual skills emerge far predates the human race even, and far predates the existence of language. And therefore, I'm very interested in how does the language can communicate with these lower level skills, where it usually happen to us in the subconscious level. So first question is I wonder how in this particular case does language interact with these low level skills, and what is the direction that you think that we can, as a community, bridge these two together?
Yeah, it's a great question. And I think that that's something that we're actively thinking about as well. Specifically here, what we've done is we've just fed it into a pre-trained policy that is language conditioned, and this is only just for pick and place tasks. So it's relatively simplistic in that way. I do think that in terms of hard, sort of really subtle manipulations that we do every day, one example that, or like, for example, pulling out my mask from my pocket and then kind of like being able to spread it out with one hand, how can you describe that with language, right? I think is relatively unclear even to me. So I think that we have a long way to go for doing these types of things. And at the moment, I think all I can say is that I think it's an open question, but it would be interesting if we can really be able to capture all the subtle sort of small motions. And I think another to that point also, I wanted to say that language models, or specifically on large language models, they carry a lot of potentially low-level common sense than you think. So for example, if you type into GPT-3, I am a self-balancing robot, I lean a little bit to the left, what should I do next? It'll tell you explicitly, I should lean back to the right. This is like an example of a low-level common sense that exists there. And I'm curious to see if we can start pushing more of that into our low-level controls. Yeah.
Thanks, Andy, for the great talk. I have a question. So you show like some of the representation are, a pixel map or affordance map, and they're really sort of action-centric. And then we also see a lot of talks today about object-centric bias built into the system. What's your view on which bias we should use more, or is there a way to combine both?
Yeah, it's a good question. I think that for object-centric representations, I think it'll be likely a mixture of both in order to achieve what we want to achieve. Because with object representations, you kind of have to design it in almost per object sort of basis. For example, deformables might rely on a different representation than if you were representing fluids. So I think that there's a fair bit of sort of engineering that needs to go in and to figure out among all of the continuum of various different object types, how do you properly represent each one and then use that as a prior? So I think that is an open question if you're going down the object representation route. The nice part is that just gains in sample efficiency are amazing. I think that if it ends up making a lot of our systems work, I'll take it any day. I think one of the values of going with a little bit less object-centric is that then it can focus a little bit more on the low-level visual cues, like geometry or colors or things like that to help you inform manipulation.
You can take one more. just telling you the sun color. Wait.
Yeah, so this is a question from Philip Isola. So language is great for generalization, but is there anything like beyond language? Like, is there anything like beyond it that's like works even better? Okay.
Yeah, I think that if there's something in which we can not describe in language and we want to generalize to, I think I can't really, well, I'm sure there are examples that exist out there, but I think that would be the limit. So thinking about that too is potentially sort of food for thought.